let's get started then. So here's the Python solution for S1. Yeah, most of you guys probably got it in the end. So it's pretty simple. It was you just read n, which is the like number of boards, and then you have like the heights of the boards. You just read the line. You split the line. It's a bunch of space separated integers, so you split it by the space character. Then you make each resulting string an integer, and you convert it to a list. If you guys haven't I basically just memorize this line because you just use it so often. But this is like a really quick way to read in a line of space separated integers. You just do input dot split by space character, and then you call map with the int and then the result, and then convert it to a list object. And then yes, then you have your heights and your widths, and the area you just have an area variable called 0, and then you iterate over all the boards, and then this is just simply the area of a trapezoid. So yeah, width times height 1 plus height 2 over 2. So yeah, that's pretty straightforward. And then you print it out, and then yeah, that works. Most people probably got that, but I think the main issue with S1 was the CPP solutions. So I have the exact same thing, but translated over to CPP. Can you guys see that? Yep. Okay. So yeah, exact same thing. Read an n. You have a vector with your heights, your weights. You read in the heights, you read in the weights, and then you put the exact same formula, and then you print the area, right? So if we just run this code here with just like a sample input, you'll see that it does indeed give the same answer as the Python. So give it a second there. So this is 18.5, right? Python will also give 18.5. But now the problem is when you go to a big input like this, I think that's all of it. Let's run it again. There's a problem with the way CPP prints the floating point numbers. So if I just paste that in, yeah. So you can see when CPP prints these floating point numbers, it does it in exponential format, and the grader basically doesn't know how to read this. Like it literally just compares like the entire integer or floating point number, like without any it doesn't parse this at all. It just thinks it's like a string and it marks it as wrong. So instead of like all this is fine, but you basically just had to do this. And then what this does, if you see out fixed before you print the double, it basically sets it basically tells CPP not to do any exponential like format the number with the floating point fixed like where it's supposed to be. And yeah, again, so if I rerun this with the big test case now, you'll see it prints the number as it's supposed to be. And then yeah, the CCC grader will mark this right. So yeah, putting a floating point number in a floating point question in S1 was kind of weird, but yeah, that's the solution for like everyone who's wondering why the CPP programs were erroring for those like 2 test cases in the middle. Okay, I think.
Question.
Oh, what's the question?
Is fixed part of the bits header, or is it just built in?
I think it's built in. Yeah, bits. Usually, most people just include this because it has everything. I'm pretty sure it's part of the standard like IO header. I forget what it is. Yeah, I don't think I'm honestly not sure. I always just include bits, but it's part of whatever the standard IO header is in CPP. Yep.
Yeah, I just checked bits isn't necessary for that.
Yeah, no, definitely not. The include bits, by the way, I think if you haven't seen this before, this is like a trick. Just get all your includes in one line. If you include bits slash stdcpp.h with like the pluses, not like pp, it basically includes like every library, like vector, algorithm, etc., into your program at once, so that you don't have to type them all out. Yeah, it's a quick hack. Any other questions? Okay, if there's no other questions, I think I'll pass it off to Kegan for S2.
My solution was overkill. I got 0.1 seconds on all the test cases, and I've heard from friends that that is not necessary. You can do a less efficient algorithm, but sometimes it's fun to do a bit more than was necessary. And in the competition, I figured I would have to do it this way, so I spent a bunch of time thinking about it. However, I will talk a little bit about how I got to my solution. So I hope you remember the problem. If you don't, it's basically you've got a grid and you flip entire rows and columns at once from 0 to 1 and 1 to 0. And then at the end, you need to count how many ones there are, basically. So I was looking at it, and you just need to find the sum rather than the actual organization. So I was thinking about how to not store the entire grid. And the first thing that I thought about was how it doesn't matter the order in which you flip them. So if you flip like these three and then these two here, it doesn't. Wait, is this the? Wait, what happened here? Oh yeah, so if you flip these three here and then these two columns, it's the same as flipping these two columns and then these three here. So the order doesn't matter. And also, what I'm sure a lot of the people who also got full marks figured out is that duplicates can be crossed out. So if row number 2 is said to flip twice, you can just flip it not at all. If you flip it 3 times, you flip it once. So those are two big sort of optimizations. And then what I got to is I started counting how much each row or column contributed to the total. So after just flipping the rows, if R is the number of flipped unique rows, there's R times n ones. It's fairly easy. After you flip the columns as well, it gets a little bit more complicated. Each of the unflipped, my final formula is here. I think this is the correct one here. There were some mistakes. But each flipped row has and contributes n minus c ones. So that's the width of the grid minus the number of flipped columns, because each flipped column is a 0. So in this case, with n is 4, the width being 4, 2 flipped columns, there are going to be 2 ones here. For each unflipped row, it contributes c, the number of flipped columns. And then you just multiply that by the number of flipped and unflipped rows. So you can do this either for the rows or the columns. It comes out the same way either time. So here are the two formulas that you get: c m minus r plus n minus c r, or r n minus c plus m minus r c. And I'm like 90% sure that these two are identical. Actually, no, I'm 100% sure these are identical because my solution worked. Anyway, so the idea is, to my solution, keep track of which rows are being flipped so that I know to cancel out duplicates, and then keep track of how many total rows and columns are being flipped, and then I can just plug it into this formula at the end. So here is my solution. I'll just go through it. Like, it's not that long. Without comments, it's 40 lines long. But first I do this, which you should always do if it's going to be big data sets. I won't go into explaining what this does because I only kind of understand what it does. So I then define some integers, the number of flipped rows, the number of flipped columns, and then my inputs here. And then I define, here's a big problem that I faced during the contest was I was getting an error and I had no clue what the error meant. So I was originally using a deck because an array wasn't working. Turns out if you've got a really big array, you have to use the new operator to put it into memory rather than on the stack. So anyway, this worked as well. So this is what I did for the contest. But anyway, this is the better way to do it. So I'm defining an array of m size, filling them both up with falses. So right now, my space complexity is m plus n bits. And then I just iterate k times. For each k, I take in the instruction. I convert the number to zero-based. If it's a row, then I flip that row instruction. So the jth row is flipped, like not equals itself. And then I also do this to keep a running track of how many rows and columns have been flipped, how many unique rows and columns have been flipped, without having to then iterate through them at the end to go through it again, because I didn't want to do that because that would take longer. And then I do that for the columns as well, and then I just plug all. This is not necessary. I was just doing that to test it out. And then I just plug it into the formula that I calculated, and that's my solution.
All right. So if you guys, some of you might not have done S3 lunch concerts, so I might go through a brief summary. So it's lunchtime at your school. I'm not going to read through this, but so you basically have n friends. And you're standing on a line. So I got like this. Okay, you're all standing on some sort of line. Okay, and you got people at certain positions, and then each person has some sort of weight, and then a distance. All right, and the way it works is that you want to find some position C where the minimum sum of each person to you is the least. So by minimum sum, I mean okay, so for example, if you have person 1, so they're at position 1, but then I'm at position 5, and they have a weight 6, and they have a distance 2. So distance 2 basically means that on either side, you can be a distance 2. So for example, to the left, you just need to be at c equals 3, and you count, and that counts as just being able to travel towards you. And then this side would be c equals 7. All right, and then weight is just the meter. What is it again? The time it takes to travel 1 meter, and this is just meters. So I'm at position 1 meter. I'm at position 5 meters. This is gonna and then I only need to be at 3 meters, so I need to travel 2 meters. All right, and then times that weight. That's gonna be a total time of 12 seconds. So we're trying to minimize the total seconds it takes each person, and then we add up how long it takes this person, how long it takes this person, how long it takes this person. That's basically what the question was entailing. Also note that the values here are very large. So we're going to have to use a long in C++. Python, you'll be fine, but it's just something to know. And they even say it here, 32-bit integer. So we have our input, sample input, and then sample output, and I'm going to be going through some explanations as to some of the theory, as a lot of people noticed a pattern in this question, but don't necessarily understand what the pattern entails. So for this question, I think the first thing we need to notice is that the value of C on the number line, is just going to be in the range of the first person and the last person. All right, because it doesn't make sense if we just have the person here, then it's just more optimal if we're already at the first person. So we're gonna notice that the minimum and the maximum positions that we should be at, for the value of C, is just at person 1 and the last person. All right, and now if we know the range of what the values of C could be, we could just iterate. We could just loop through every single value, the sum of all the times, just at every single position from the minimum, from the first person to the last person. And this solution would only get us 4 out of 5 marks. So in order to optimize this, we need to make it so that we're not calculating the time for every single person. And in order to optimize this, people noticed a pattern. So I actually graphed this out for you guys. I'm actually taking data management. So here is a graph of actually one of the test cases, and the values of C. And when you look at this, you can really notice there's kind of a pattern here. So like this is the position of our first person and the position of our last person. If you guys didn't know, the positions are from 0 to like 1, as you can see here, like 1 billion. So there's no negatives. It's not like a number line. It's just like 0 to 1 billion. So as you can see here, it seems like there's a pattern. It seems like as we get to the ends and we continuously go to the middle, at some point at our minimum, we get to like a minimum right here, as you can see. And for our other test cases, this is also the case. For our smaller test cases, as we go from the ends, we just get to our minimum, like this as well. So then from this, people would have actually noticed that there was this trend by doing the iterative solution, by just getting all the values of C and then finding a pattern, if that makes sense. Now, the thing is, though, is that we don't know necessarily why this pattern arose. So with this pattern, though, we can optimize it by using binary search. And with binary search, we're able to get 15 out of 15 marks. So for example, we would take the two ends, and then binary search works where we go to the center point, and then we look left and right. And since it's always decreasing on either end, we just need to check which side is decreasing. So then we would look to this side, and then we would cut in half the data, and then look at the center there, and then we see, oh, this side is decreasing, so then we cut it in half. So then we look at this point, and then we get so to the point where we are at the minimum point. And we can detect if we're at the minimum point if to our left and to our right we're both increasing or they're the same. As you can see, with this data set, we just get to the point where all the data points are just the same. All right. Now, question we might be wondering about is how and why does this pattern arise? And I actually have an explanation for this. So as you guys saw in this graphic, we can either start at, now just when we're starting off, like at our left point or on our right point, the trend is that just in a general case, I have to cover this first, my bad. But if we just put a point at somewhere, just on this number line, we're going to have people to the left and people to the right, all right? They're going to have their different weights. So weight 1 is for person 1, weight 2 is for person 2, and weight 3 is for person 3. All right. So the thing about this is that if we move to the right, we're going to be decreasing our value of C by weight 4, weight 5, and weight 6. So the sum of all of these weights on the right. And we're going to be decreasing all of these by 1. Weight 1, weight 2, weight 3. The reason why is because we're now 1 meter longer. Like the distance is 1 meter longer to weight 3, to weight 2, to weight 1. All right? So with this in mind, we can tell that when we go to the right or we go to the left, that we're always going to be decreasing our value on one side, going to the right, and increasing the value if we go to the opposite side, or if the sum of these weights and the sum of these weights are equal, then we're at a minimum. Then it doesn't matter. We've gotten to our minimum. All right? Now, the only time this kind of scenario changes, as we go and go and go and go, as you can see here in our second diagram, oh no, we passed weight 4. When we pass weight 4, the the distance that we decrease and the distance that we increase, not the distance, the time changes, because now we have to compare the sum of W5 and W6 to W1, W2, W3, and W4. So then another solution that actually someone found out is that because of this, we've discovered that we just have to check near every position of each person and see if that's a critical point, if that's a point where we are at a minimum. Because at some sort of point, we're going to be flipping the sums of these two. So this is going to be larger and this is going to be smaller. And then this is going to become large and this is going to be smaller. So for example, if we have weight 1 is 2, and this is 3, and this is 4, this is 7, this is 8, and this is 9. So of course this is going to be sum of like 10, 15, 24. This is going to be a sum of 24. Alright, so then as you can, this isn't a good example. But as you can see in this example, if we move left, we'll just continuously move left because we can see that, we'll be continuously moving right because we keep decreasing in a larger number, alright? And eventually, once we get to here, then the sum of our left values will be 2, 3, 4, and 7. And then the right values will be 8 and 9. So then 2 plus 3 plus 4 plus 7 is actually going to be more than our right side. So then at this point, we've flipped both of them. So as we continuously go right, then we're going to be continuously increasing. So this is my rough explanation of how this can occur. Now one question that might be posed is, oh, but why aren't there multiple minimum points? Well, the reason why there's no multiple minimum points is because in order to have like multiple minimum points, we're gonna have to have some sort of graph, kind of like this. You know, there's gonna be a minimum, but there's also gonna be a maximum, right? And we can't have any maximums actually, because as we discussed earlier, with the weights on the left and the right, either they have to be equal or one is smaller than the other. So that means that we can't have a maximum because both sides can't be smaller than this point, than the total time when we're at this point. Okay, so then this diagram, this diagram, so the point of this diagram is just to show the behaviors of the very left side and the very right side, as I showed before. So when we're at this point, keep going right, we're just going to keep decreasing and decreasing because the sum of all these weights is definitely going to be larger than this weight. And just vice versa for this side. So then if we just look at our data, so then both of these sides will keep decreasing and they'll get to a certain point after we change the weights on each side, so what is on the left, what people on the left and on the right. Eventually at some point we'll flip them and we will get to our minimum. So here's some of the smaller diagrams. I've added points actually as well for a bigger explanation. Another solution that people had was doing just a sweeping line method, where basically, as I mentioned before, you can find these critical points, so the positions of the people. So these orange dots are the positions of the people, and then we have some sort of value d, right? So you're still technically have a distance of 0 when you're in that radius d. So then we just add those points. And as you can see, all that people had to do was go to each of these critical points and then iterate to the left and the right d number of times, and then they would be able to find the minimum values. And this just decreases the number of searches we need to do. So as you can see here, for this point, it would just be black, but then for this middle point, the yellow on the left and the right. So then we get to a minimum point, and then here we just be the green. So then now we found the minimum point. So this was another interesting solution we had. Okay. I've talked a lot. And hopefully that was clear enough, I guess. But I'll get to the code now. All right, with the code, as I mentioned, we're going to be using binary search. And we're going to be going through all values of C. So as you can see here, I just included bits, std c++.h, using namespace std, and then I just, this is just for long long. Long long is just a larger integer, and then I also have defined just the maximum size of an integer. I'll get to that as to why I did that later. So then I define a vector, a 2D vector of friends. So this is just a vector of friends, and then this inner vector is going to be a size of 3, and it's going to contain their position, their weight, and their d value. So like the distance you need to be from like the radius around your position C. I also have.
I'm going to quickly jump in and make sure everybody knows that attendance is up. So make sure to head over to the announcements channel and click the white check mark. I have been having some problems with inaccurate bot DMs. It'll tell you that you're not verified when you are. So if it says that you're not verified in a DM, head over to the bot bot commands channel, and check your attendance using ~attendance. Thank you.
All right, I'll continue. So now we have our function compute time. I didn't really go over this, but I'll go over it now. All right, so we're just going to do a total time. So because we need the time of each friend, so we need to sum that up. So then for each of our friends, we can just get the p value, the w value, and the d value, just iterating through this vector. And then, as you can see here, if the person's already in the radius, we continue. So in order to figure out if they're already in the radius, we get the left distance. So as I showed before, so the left distance in here would be c = 3. So the position, the minimum position you have to be at in order to count as being near you. And then the right position, left distance would be 7. So it's less of a distance and more of a position, I guess. The left position we have to be. Okay. So left distance is smaller than p, and then p is smaller than the right distance. So we're in the radius, we're in the position. We continue. So we can skip that. Then in order to calculate the distance, we get the absolute value of p, so the position of our friend, minus the left distance, so the minimum position you kind of have to be at. And we get the absolute value because we can get negative values if the friend is on the right or the left, that type of thing. And we get just the absolute values of the right distance and the left distance and the minimum. And then after that, we get our minimum distance. So then we add that, so our distance that we need to travel, and then we times that by our weight because we travel 1 meter, so 1 unit of distance per w seconds. And then we return our total time. And you can see here I used long long because c is going to be a very large number, so long longs. I use a lot of long longs. Long long. And then here's our main code. So iOS sync with Studio and sin.ty 0. Kegan didn't go over this, but I believe these are just for optimizing your input and your output. And then I define my integer n, the long longs pwd, and then the reason why I have the left and the right here is for binary search. So left is our minimum value of c, and r is our maximum value of c. Did someone unmute themselves? Did they have a question? I heard something. No? All right, I'll continue. And the reason why I have long, even though it's supposed to be minimum value, and I've set it to the actual maximum value of the question of what p can be, the reason why I did this was because I'm going to be setting L and R to the first value of our first friend, because I know that there's going to be a minimum of 1 friend. So then this is always going to evaluate to the first friend. And this is always going to value to the first friend. And then from there we can just get our minimum position from the left and the minimum position on the right of that number line. So for each friend, we receive the input, we push back. Oh god, the autoplotting? Okay. Was there an issue? just curious. All right, and then I'll just continue. On the first iteration, though, L and R become the position of our first friend. And then if our position of our friend we received is greater than or equal to our current range, we'd reduce the range from the left or the right. Okay, and then as you can see here, if our friend's position, this is going to be their position, is greater than our R value, then R is going to be this. If it's smaller than our left value, then its left is going to be this. And all right, so now we have a range of C values we need to do. This is just now we could do 1 to 100 million, but this is just more optimal. All right, our current time, I set it to int max because I want it to be greater than any value it can be. So then, because we're going to be computing it later. Okay, so our naive solution is just to search through every value and then just make this the largest value it can be. Oh yeah, and this might be a blunder. Since I've set this to long, I don't think this should be the maximum integer. This should be the maximum of the long. But it still works for the numbers of the question, so I'll note that in mind. And then binary search for our full points. This is just a classic binary search. If the left position is smaller than or equal to the right position, then we calculate the middle. So we add them together, divided by 2. And then we compute the current time with the middle. And then we look at the left and the right side. We look at if the left side is smaller than our current time, then we're going to move our window to the left side. So that's basically our largest value is going to be this middle minus 1. And then else if, right here, compute time, mid plus 1 is smaller than current time. Then we're going to move to the right. And then if that's not the case, if none of these are smaller, then we're just going to break this loop. And then we just output our current time. All right, I think that's my solution.
All right. So the question states that Toronto has n subway stations that are numbered from 1 to n. So you start from station 1, and every day you need to reach the station n to get to school. And there are W one-way walkways running amongst the stations, the ith of which allows you to walk from station A, I, to a different station B, I in 1 minute. So there can be multiple walkways connecting any pair of given stations. And there's also a subway line that follows a certain route through the n stations, starting from station 1 and visiting each station exactly once. And initially, the route consists of the stations S1, S2, all the way to Sn in that order. So there will be an input. We'll go through that later. And yeah, this sequence of S's is a permutation of the integers from 2 to n. And this is the route that the subway takes. And only one subway train runs along this route per day, departing from station 1 at 6 a.m. in the morning. The time doesn't really matter. And it takes 1 minute to reach each subsequent station. So walkways take 1 minute to go between stations, and subway routes take 1 minute to go between stations. Which means that this graph, it's a graph theory problem, if you guys didn't already know. So we're doing some graph theory. And since both the subway and the walkways take 1 minute, this is pretty much just an unweighted graph. So we don't need to do Dijkstra's or any of that, I think. So over a period of d days, the subway lines, the subway route actually changes. And what happens is each day, you get 2 integers, x and y. So on the ith day, you get xi and yi. And then the xith station and the yith station swap on the route. So for example, I'm going to write this out. If you had the route 1, okay, that's not a brush. If you had the route from 1 to 2 to 3 to 4 to station 5, and let's say on day 1, then stations 3 and 4 got switched. Actually, wait. This ordering is pretty bad. I'm going to do it more randomly. So let's say you had the route that goes from station 1 to station 3 to station 4 to station 2 to station 5. Let's say this is the route. And on day 1, the route swaps the 3rd and the 4th station. So 3 gets swapped with 4. Well, then on day 1, the route will become 1, 3, 2, 4, 5, because the 3rd station, I'll use a different color, the 3rd station and the 4th station got swapped. And then now we have this new route that we can take to get to school. And pretty much the goal of this problem is, given all the stations and all the walkways between the stations, and given the subway routes for each day, we want to find the minimum number of minutes that it takes for each day. So let's take a look at the input. I'll just erase all that. Okay, I think I just accidentally, there we go. So the first line contains 3 space-separated integers, which is n, w, and d. So n is the number of stations, w is the number of walkways, and d is the number of days. The next w lines, we get a and b. We get 2 integers a and b, which are just the from station and the to station for each walkway. And then after that, we get a line of n space-separated integers, which is the initial permutation of the stations. So that's the initial route. And then for the next d lines, so for d days, we get 2 space-separated integers, x and y, which represent the swaps. And then ignore this line. We don't care about bounds for this part. Okay. So the output, we want to print d lines, 1 for each day. And for each line, for each day, we want to print the minimum number of minutes it takes to get from station 1 to station n. So let's take a look at this input. So we get n, w, and d. So there are 4 stations, 3 walkways, and 3 days. Let's draw this graph out. So we have 4 stations, so let's just draw them out here. And also, this question likes to count from starting from 1, but I like counting from 0. It doesn't really matter. I think it's just a matter of preference. But for this, I'm going to convert all of them to start counting from 0. So you'll have like a station 0, station 1, station 2, and station 3. And the first line of input connects 1 to 2. So, whoops. I gotta remember that this is 1 higher than this. So this actually connects 0 to 1. And then this connects station 3 to 4, which in my thing is 2 to 3. This connects 4 to 1, which is 3 to 0. So this is what our walkways and our stations look like. And the initial permutation is of the stations is 0, 3, 2, 1. So the subway travels from 0 to 3, then 2 to 1. And that's the route for that day. And then we get our swaps for each of the 3 days, which is we swap the 3rd and 4th, we swap the 4th and 2nd, and we swap the 3rd and 2nd. So let's write those all out. We end up with 0, 3, 1, 2 is our next route. Then we end up with 0, 2, 1, 3. Then we end up with 0, 1, 2, 3. And remember that we print d lines, so we actually don't work with this first initial permutation. So we have 3 outputs, which I'll show is these. Okay, so how should we go about solving this problem? The first thing that we need to notice is that the minimum route can always be, let's say, first you take the subway, and then you hop off and take and then you take the walkways. So I guess in other words, that's saying for the minimum routes of each day, you always take the subway first, and then you take the walkways next. Or it's always possible to do that. Because say if you had if you want to go from 2 to 0 and you had a subway line from 2 to 0, well, it's always faster to just take the subway from 2 to 0 than to go the walkways from 2 to 3 and then 3 to 0. And I think that's how you're supposed to prove that. but basically it's just you go subways first and then you go walkways.
All
And
right.
then the next thing is I'm just taking a look at my notes here.
I was
Alright.
gonna,
Oh yeah, what's up, Kevin?
I was gonna interject. So I believe the subway will move, at will move as well as while you're walking on the walkways.
Yeah, it will.
So that's something that you have to know, and that's why it's only optimal to just be on the subway the entire time, I believe, or like do the walkways
Yeah, so
and then
basically
subway.
subway first, then walkways. Yep. And you might end up with a situation where it's like you can take a subway or a walkway, but you can still take the subway. So yeah, subway first,
Wait.
walkways next.
I'm not sure I understand what you mean. So you're saying that after you get off the subway, you're not going to get back on it?
You can't get on it because it's not optimal because the subway
Yeah.
takes time. So for example,
Yeah.
if you get to station 3 using the walkways in like one minute, but then like the subway takes 3 minutes, then you're just gonna be stuck at 3 and you're just gonna be waiting for the subway. So no matter in that situation, it's just gonna be the same as traveling on the subway.
Okay, I figured
Yeah.
that's what you're talking about. I just wanted to make sure.
Yeah. That's what we're talking about. And then
I guess the
that's
illustrated is like, yeah, like Kevin said, the subway moves in parallel with you. So say like if you're going from 2 to 3 and then the subway goes from 3 to 0 and you want to go from 2 to 0, then well, you could take the walkways, but the subway moves alongside with you. So it really doesn't matter whether you take the walkways or the subway.
yeah. So the
And
only
yeah, like Kevin said, if you take a more inefficient route, like if you want to go from 2 to 0 and let's say the subway goes then from 0 to 1 and then 1 to 3. If you went from 2 to 3, well, when you get to 3, the subway will be at 0. When you get to 0, the subway will be at 1, and you won't be able to get back onto the subway.
So I believe the only way to optimize our route is to check if, like at the end, we can just use the walkway.
Yeah, so like I said, subway first, walkways next. After
Yes.
walkways after.
All right.
All right. So what I did for my solution is, well, you start from the final station, right? The destination station. And what you can do is you can do a breadth first search and find the distance from this or the number of steps it takes from every other station to get to this station. So yeah, like I said, the way you would do that is with a breadth first search, you would flip all of the edges. So let's redraw this graph. Let's see. So 3, 0, 1, 2. That is really ugly 0. Then all of the edges get flipped. Yep. And hopefully the end goal that we want to get to is we get an array, and I'm going to draw the indexes on the top in red. So 0, 1, these are the array indices. And the end goal is we get an array where for each station, which is represented by this index, I guess, we get the distance from that station or the number of minutes it takes to travel from that station to the final station. And in this case, it's really easy to find this just by looking at it. So 0, it's for station 0, it's impossible to get to station 3, and same thing with 1, just by walkways. So this isn't accounting for subways. So what we do is we would place infinity here. Basically, I'll show how to represent that in code later. Basically, we just use a really big number. And then we see that it takes 1 step to get from station 2 to 3. So it takes 1 minute. And then it takes 0 minutes to get from station 3 to 3. So 0 minutes. And I call this array the mask. So the mask in air quotes. and we'll see why in a bit. So the way we would actually compute this array programmatically is, like I said, we'd flip all the edges, then we'd start from 3, and then we do a breadth first search until we run out of vertices to visit, and then we'd find the minimum distance from 3 to each of these vertices. So in this case, the breadth first search only reaches 2, so we get 1 for 2 and then 0 for 3. And we maintain like a distance, maintain a distance vector. No, not vector, a distance array for each of the stations, and that array would end up looking like this mask. Okay. So the next thing we want to do is we want to figure out a second array. So let's do this numbering thing again. So station 0, 1, 2, 3. And this array will, at each index, will show us the number of steps it takes to get to that space, to get to that station by taking the subway. So for example, on day, let's ignore this one. On day 1, so this is day 1, the subway goes from 0, 3, 1 to 2. So this array would look like, well, it takes 0 steps to get to 0, since 0 is the first station. And then to get to 3, it takes 1 step. Then to get to 2, to get to 1, it takes 2 steps. And then to get to 2, it takes 3 steps, or 3 minutes. And then what we can do with these two arrays is we can add the mask. Like we can do element-wise addition and add the mask to this array that shows us the number of subway stops that we need to take to get these stations. So 0 plus infinity, we're just going to say is infinity. Same thing with 2 plus infinity. Then 1 plus 3 is equal to 4. And then 0 plus 1 is equal to 1. And what this sum shows us is the total number of steps it would take to get to this station. So, for example, station 2 would take 4 steps. If we took the subway to station... Wait, sorry, no, I said that wrong. This array shows us the number of steps it would take to get to station 3, so the final station, if we take the subway first to this station, and then we take walkways for the rest of the way. So what I mean by saying that is, for example, let's say we take the subway to station 2. What happened is, well, it's on day 1, so the subway route looks like this. Go from 0 to 3, and then 3 to 1, and then 3 to 2. So we first take the subway to station 2. So that's start from 0, 1 step, 1 minute, 2 minutes to station 1, and 3 minutes to station 2. So that's 3 minutes here, and then we take the number of steps it takes to get from station 2 to station 3 with walkways, which is 1. And we add those two numbers, and it ends up taking a total of 4 steps to get from here, station 0 to station 3, by taking the subway to station 2 and then taking a walkway to station 3. And then same deal with 3 here. So on the subway route, the subway goes directly to 3. So it takes 1 step to get from station 0 to station 3. And it takes 0 steps to get from station 3 to station 3 using walkways. So basically, once we have this array, we just need to find the minimum. And then we get our answer for that day. And then we need to do it for a bunch of days. So yeah, so we already have each of these days, and then we can just repeat this process of computing the number of steps it takes for the subway to get to each station. And then we can get this sum, and then we get the minimum, and that's how we get our answers for each day. So let's take a look at the code. I forgot to mention this. This is also a partial solution for S4. I think I only got 7 out of 15 points.
Yeah. So the reason why this is partial is because the algorithm for the breadth first search is not efficient enough for this solution. So I believe in order to optimize this, you need to be able to have a better way of finding the distances from to the nth node. And I believe in the Discord they mentioned a segment tree. That's the data structure you use for.
All right.
For
So
finding
if you let me continue. So yeah, actually, I think the breadth first search should be okay. It's just that on the bounds, I think there was like a maximum of 200,000 days too. So after computing, I think they called this a prefix. So the mask, after computing the mask, you'd use something like like Kevin said, a seg tree or a multiset, or some sort of data structure that I didn't really research before doing the CCC. And then you would use that and optimize computing the minimum for each day. All right, so yeah, I just started off with the basic, with some basic stuff. Like I define LL as long long. I use long longs, but I think ints are okay for this problem. So we take the inputs of N, W, and D. And then I made a vector of vectors for an adjacency list. And then I initialized the mask. So, oh wait, yeah, I can't switch back to paint. So I initialized the masks, and in this case, I initialized everything to infinity for now. And in this case, I just called infinity to be like 100 million. And then I made a vector called perm, and perm is the route of the train, of the subway. And one thing that I didn't get to mention in the paint thing is you can actually find the number of steps it takes to get to each station by just finding like the array inverse of perm. I think that's what it's called. Basically, just swap you swap the stations, so the elements in the array with the indices. So, for example, if you had station 3 at index 1, then this array would have 1 at index 3. All right. And then for the adjacency list, this thing just assigns a vector, an empty vector for each station. And then we take the input for each connection. So right here, what I did was I actually flipped all of the connections. So yeah, there's that. And then in this part is computing perm inv for the initial permutation. So we take the input for permutation and then we set each element, we set perm inverse to. And then here is our breadth first search for computing the mask. So we have a DQ, which we use as a queue. Then we have a vector of booleans, which shows us which stations have been visited already. And then we just push back the last station, so our destination station, into the queue. And then in the visited vector, I made it so that it's 1 smaller than its actual size and filled it with falses. And I just push back a true so that it gets to its actual size. And then the true represents the final station. So we've already visited that one. And then for the mask, for the last station, we set to 0 because it takes 0 steps to get to the last station, starting from the last station. And here's our while loop for the breadth first search. So you pop out the first vertex, and then for each vertex that's connected to the first vertex in the adjacency list, if that visited, then you push that vertex to the queue. You push it to the front. I messed up. I wasted a lot of time because I accidentally did push back. Yeah. So that's cool. And then mask, what you do is for the distance. So I'm going to call this distance actually. The distance to get from V2 to the final station is just the distance to get to V1 from the final station to the final station plus 1 because they're adjacent to each other. Right, I guess. I'll put in more detailed comments later. And then you just set visited for vertex 2 to be equal to true, and then that's the end of the breadth first search code. And then over here, I actually made a vector of pairs, which stores all the swaps. Yeah, so I took the input of all the x and y values and just pushed them back into the swaps so that we can work with them later. And then for all the swaps and swaps, I got those the x and y values. Then I swapped each station on the route. So station X with station Y on the route. And at the same time, also made it swap the perm inverse too. So yeah, that happened, and this gives us an accurate perm inverse list, or the number of steps it takes to get each station from the subway. And then basically what we did is we would just pretty much scan through each element. So we have L long max, which is the max long value, equal to out, and then we try to compute the min for the sum of mask I plus perm inv I for I equals 0, where I is less than mask.size. And then, yeah, once we find that min, which is equal to out, then we just print that out, and then we go on to the next iteration. And that's pretty much how the code works.
Okay, so this problem, basically, we need to find a bunch of, we need to create a sequence of integers, a1, a2, up until an, and we're given some constraints. That like some subsequence, like a3, a4, I don't know, something like that. We have to make the GCD of this some number, like 2. Like you'll have like a list of like subsequences, like
All right.
3 to 6, and is like a GCD of 2 or something.
All right.
And then like 1 to 3 has like 5 or whatever.
All right. Sounds good. I was just trying to clarify so that everyone's on board. I think we need.
Okay, so the trick here is to go backwards. We really want to find the prime factorizations of the sequence instead of like some other way of representing them. And the reason you'd want to think of this is that if you have like 2 integers and we know their prime factorizations, just for example, like these two, then the GCD, we can compute the GCD by just looking at the prime factors and taking the minimum of the exponents. So the GCD of x and y would be 2 squared times 3. Yeah. So what we do is for each number in our sequence, we want to.
Wait, can I go now?
Yeah.
3 o'clock is completely optional.
Attendance has already been down. I mean, up. You're free to go. It's just we're explaining S5 if you were curious about it.
Yeah. So we want to basically do something about the prime factorizations of these numbers. So this is like exponent of 2, 3, 5, 7. And if we had, like, for example, the GCD of A1 to A2 is like 4, then we know that the minimum exponent for 2 has to be 2. Like, does that make sense?
Sounds good, Tian.
So yeah, if this was like 3, and the minimum of these has to be 1. So in short, you just go through every one of the intervals, and you want to like push these numbers as high as possible. I mean, like as low as possible. So this has to be at least 2 in order to satisfy this. And sometimes things might not work. So one example was the GCD of both of these is 2, and the GCD of just one of them would be 5. This doesn't work. So the power of 2 for these ones has to be at least 1. And the power of 5 for this one has to be at least 1 as well. But if we look at A2 here, we really want this. We need this exponent to be 0 in order for the GCD of 5. But this isn't possible because we already pushed it to a minimum of 1. So you just go through every interval, and you push all of these exponents as high as low as possible, and then you just go through every one of the intervals again, and then you check if any of them fail. And if any of these fail, then it's impossible. And if all of them work, then you can just calculate the numbers. Like this would be 2, and this would be 10, for example.
All right. With that, guys, yeah, like we said before, that concludes our CS Club meeting. If you guys are still here and still listening, next week we'll be covering artificial intelligence. You'll be able to create your own neural networks to do some cool things.
As quoted by the very wise man Kevin Gao, it's machine learning.